Are we going to stop soon?
We don't need to. My new Kia Sportage Hybrid can go up to 775 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 Kia Sportage Hybrid can go up to 775.
Hi, it's Mr. Anderson. Today I'm going to be talking about plate tectonics. What's always interested me about plate tectonics is it's a fairly recent science. In other words, not until the 1950s were we sure that the plates were actually moving. One of the first people to suggest that was Alfred Wegener, and he actually worked right around 1920. And what he said is that if you look at the different continents, here's North, South America, Africa, Eurasia, they tend to fit together on almost like a puzzle. And so he was the first person to say maybe all of the plates were connected at one point. We now know that that's true and that that was called Pangea. The problem is that Wegener thought that the continental plates, which are actually really large, and the oceanic plates, that the continental plates were somehow pushing their way through the oceanic plates. Oceanic plates are really dense, and so other scientists at that time said that they wouldn't have the momentum to be able to push through the rocks, and so the theory kind of fell apart. And so Alfred Wegener actually didn't spend most of his career studying plate tectonics. He ended up being a meteorologist for most of his career and ended up dying in Greenland. It's a crazy story of how he met his end. But that's not what I'm going to talk about. I'm going to talk about plate tectonics. So when did the science really take off? Well, there were two things that took place. First of all, we started looking at fossils on one side of the Atlantic and on the other, and we find that they actually matched up. So that's a good piece of evidence. But the best evidence came by looking at the rock in the oceanic crust, so in the floor of the ocean. There's rock underneath the water. And we started looking at the magnetic fields that are stored in the rock. So as the rock is actually being formed, we can look at the magnetic pole or the polarity in the rock itself, and our poles will actually switch back and forth. So that occasionally north will become south and south will become north, and that's actually recorded in the rock. And so we could look at how old the rock was, and we could see how fast it's actually moving. And so this is a cool study because this right here, to kind of wrap your head around this is right down the middle of the Atlantic Ocean. These are going to be the youngest rocks. So in this diagram, the youngest rocks are going to be in red, and then the yellow is going to be older, and then the green is going to be older yet, and the blue is going to be older yet. So what does that mean? Well, it means that the youngest rock are actually right at the center of the ocean, and then it's older the farther we go to the edges of the Atlantic. What does that mean? Well, it means that North America and Eurasia were connected, and they've been pulled apart, but they're not plowing through the oceanic crust. New oceanic crust is being made in the middle, and so it's actually pushing them apart. Now, how fast does this happen? I remember reading once that the plates move about as fast as your fingernails grow. And so you're not going to see the plates moving, but over millions and millions of years, it actually ends up being quite a bit. Now, another way to look at where those plates actually exist is to look at where earthquakes occur. And so earthquakes occur where you have rock either being pulled against itself, pushed against itself, or sliding past itself. And so when that rock gives a little bit, that's an earthquake. And so if you look at where the earthquakes are centered on our planet, they're actually centered, well, here'd be the Atlantic, so right along that mid-oceanic ridge. We also see them around what's called the Ring of Fire. So if this is the Pacific Ocean over here, so this would be Alaska down the eastern seaboard, or excuse me, western seaboard. This would be the San Andreas Fault all the way down to South America, and then all the way back to Japan again. So we have what's called this Ring of Fire. Now, why do we find earthquakes in some areas, but in some areas we don't? Well, that's where the plates actually match up. And so if we look in the U.S., which we're pretty familiar with, where would we find a lot of earthquakes? Well, in California. So why do we have so many earthquakes in California? Well, here's the San Andreas Fault. It actually cuts California right in half. And so on one side of that, we have a plate moving in one direction. On the other, it's moving in the other direction. And so when they slip past one another, then we actually have a earthquake. And so these are the major plates on our planet. We have like a North American plate, a Pacific plate. This is the Juan de Fuca plate right up here. But all of these plates, as they move, shape our planet. And they also give us earthquakes and show us where plates, as they move, Juan de Fuca plate right up like a North American plate, and show. So for example, it's had a huge earthquake in Japan, which causes a great tsunami. Why is that? Well, it's right here located on the junction of almost 4 plates that are all moving past one another. And so plate tectonics tells us that plates are moving on our planet, but there are 2 types of plates that you should be familiar with. The first one are called continental crust or continental plates. Continental plates in general are made of granite. Now granite, the best way to think of granite, if you've ever been to Yosemite, this is a giant piece of granite. Granite is going to be a lighter rock. Continents are very big, so my fist is going to represent a continental plate. And they're also a little less dense than the oceanic plates. So this is oceanic plate. This is from lava forming in Hawaii. Oceanic plates are made of basalt. And so basalt is going to be
Charlie's having a friend over.
is it's a fairly recent science. In other words, not melt as it moves farther and farther down and eventually causes volcanoes. So it's melting and then it's causing boundary it is between the 2 continental plates. So first of all, or oceanic plates. First of all, let's think about what could geology planet. So let's say we have 2 continental plates that are coming together. Well, they're both massive and they both have roughly the same density. And so when they run into each other, it's almost like 2 cars running into each other. They'll just crumple up and get larger. So where's an example of that on our planet? The Himalayan mountains, which is formed where India is climbing into Asia. So that's 2 continental crusts. What else could happen? Well, we could have 2 continental plates that are actually pulling apart. We call that a divergent boundary. What does that create? That creates a rift. In other words, when 2 continental plates pull across from each other, that causes a rift. And so the Rift Valley of Africa is an example of 2 divergent continental crusts. What else could happen? Well, we could have 2 oceanic plates converging. So what happens when we have 2 oceanic plates converging? Well, one of them will tend to buckle under the other, and then we get volcanism as well, and we're going to have islands forming. And so if you look at the Aleutian Islands, which caused that arc off of the coast of Alaska, it forms like this. We have 2 oceanic plates running into each other, one's being forced under the other, and then you get this volcanism. What happens if we have 2 oceanic plates that are moving away from each other? Well, what's that? That's seafloor spreading. So right here in the center of the Atlantic, remember, we have 2 oceanic plates that are moving past one another. And remember, the Atlantic will get bigger and bigger and bigger just as a cause of that. And then we could also have a transform boundary. That's when one is sliding past it. An example of that would be the San Andreas Fault in California. So the one thing I have told you is that that's how we get all the geology on our planet, or the rock formations on our planet. But what I haven't told you is what causes that. So what causes that is convection currents. In other words, this is magma down here, so this is molten rock, and so we have convection currents. And the best way to think of that would be like in a lava lamp, where you have the oil moving up and down. So you get convection currents where we have hot areas moving up, cool areas moving down, and that's actually driving the movement of these plates. One other thing that I haven't talked about is what's called a hotspot, and those are kind of pretty cool. This would be a hotspot right here. So Hawaii is actually formed by a hotspot. That's just an area where the magma happens to come a little bit closer to the crust. And so Hawaii is formed by a hotspot, but really close to home, Yellowstone Park is actually situated over a hotspot. And so as the crust moves over it, that hotspot stays in the same location. And so Yellowstone Park will actually move its location over time. We can track where it was in the past, just like Hawaii will move. The big island of Hawaii is where that volcanism is actually taking place. And the reason it trails off to the edge of Hawaii is that there's been more erosion. And so that's a brief introduction to plate tectonics, but I hope that's helpful.
Always been a
Build it like Beckham. You know you missed this spot, right?
Whoa.
What's that?
I just built a budgeting app in Base 44.
Guys, Nina just built an app.
Impossible.
We humans of planet Earth benefit from a great coincidence. It's a coincidence of time and of space and of math. The coincidence is this. The sun is about 400 times wider than the moon, and it's also, on average, about 400 times farther away than the moon. The apparent size of an object in the sky depends on how big it is and how far away it is. So these numbers being equal means the sun and the moon appear to be about the same size in the sky. And that's where another interesting thing comes in. Sometimes the moon passes directly between the Earth and the sun. It doesn't happen all that often, but when it does, you get magic. Or even better, you get science. You get an eclipse. An eclipse is a generic term in astronomy for when one object passes into the shadow of another object, darkening or blocking. A solar eclipse is when the moon blocks the sun, casting a shadow on the Earth. And a lunar eclipse is when the Earth blocks the sun, casting a shadow on the moon. But how do they work? Well, the moon orbits the Earth once per month, and the Earth orbits the sun once per year. If the moon's orbit were perfectly aligned with the Earth's, essentially sharing the same plane, we get a solar eclipse every new moon and a lunar eclipse every full moon. But we don't. That's because the moon's orbit is tilted with respect to the Earth's by about 5 degrees. What that means is that at new moon, the moon can be as much as 5 degrees away from the sun, passing above or below the sun in the sky, thereby missing it from our perspective. But sometimes the moon is in the right place at the right time, and at new moon, it lies perfectly in line between the sun and the Earth. And when that happens, we get a solar eclipse. This geometry happens at least twice per year, and sometimes as much as 5 times per year. What's happening physically in space is that the moon is casting a long shadow. Usually that shadow misses the Earth, but during an eclipse, the moon shadow falls on the Earth's surface. In fact, there are 2 shadows from the moon, one inside the other. One is a narrow cone tapering to a point away from the moon. If you're anywhere physically inside this cone, the moon appears big enough to completely block the sun. That means the shadow is very dark, and we call it the umbra, which is Latin for, you guessed it, shadow. Outside of this deep umbral shadow is a wider conical region where, if you're in it, the sun is only partially blocked. You can still see some of the sun past the moon. You're getting less light, and so you're technically shadowed, but it's not quite as dark as the umbra. This region is called the penumbra. Pen in this case for Latin meaning almost or nearly. When the umbra touches the Earth, we get a total solar eclipse. But what does that look like from the ground? You don't get a total solar eclipse right away. First, the edge of the moon slips in front of the sun, and we see a little dip in the sun's limb, its edge as seen from the Earth. That's the start of the penumbra sweeping over you. As the moon slowly moves, that dip grows, becoming a bite. The sun becomes a thick crescent, then a thin one. As the sun becomes an ever thinner crescent, the sky begins to darken. Then, finally, the moon's black disk completely covers the sun. The umbra sweeps over your location, and at that moment, totality begins. You might think that this just means the sky gets dark, and it's like night outside for a while. But a total eclipse is far more than that, and that's because of the sun's corona. As I'll cover in more detail in a future episode, the corona is the sun's atmosphere, an ethereally thin envelope of gas that stretches from the sun's surface into space for millions of kilometers. It's really faint, and therefore usually completely overwhelmed by the intensely bright light from the sun. But when the moon blocks the sun's face, the corona becomes visible. It surrounds the sun, filaments and tendrils extending into the sky, an incredibly beautiful sight. I know many people who have said it's the most spectacular thing they have ever seen. And there's more. The moon's edge isn't smooth. There are craters and other depressions. Craters right at the moon's edge allow sunlight to stream past. We see these as bright patches around the eclipsed sun, which are called Bailey's beads, because they were first described by English astronomer Francis Bailey in 1836. Because the moon and sun are very nearly the same apparent size, totality is brief. The longest it can last is only about 7 or 8 minutes. That's how long it takes the umbra to move over one spot on the Earth. When totality ends and the moon starts to move off of the sun's face, for a moment, just a single spot of the sun is unblocked, glowing fiercely on one side of the moon. Sometimes you can get a circle of light around the moon's surface, and together with the bright spot, it looks like a celestial wedding ring. In fact, this is called the diamond ring effect. Then, inexorably, the moon pulls away from the sun, and the order of events is reversed. The umbra is gone, but you're still in the penumbral shadow. The sun shows a thin crescent, then a thick one, then a dip in its side, and then it's all over. The umbral shadow of the moon is pretty small where it hits the Earth, so a total eclipse is a local event. If you're too far north and south, you don't get a total eclipse, you only get a partial one, which is still cool, but lacks the mystique of a total eclipse. Remember, too, that the moon's orbit around the Earth is an ellipse. That means sometimes it's closer to the Earth and sometimes farther. If a solar eclipse happens when the moon is at the far end of its orbit, it can actually be smaller than the sun in the sky. It doesn't block the entire face of the sun, and it leaves a ring of light around the black circle of the moon. The technical name for this shape is annulus, so this event is called an annular eclipse. A lot of people think if you look at a total solar eclipse, you can go permanently and completely blind. That's really not true, but some parts of eclipse watching are more dangerous than others. I mean, obviously, it's not a good idea to stand there and stare at the sun. Looking at even the uneclipsed sun for more than a moment is painful, and that pain is the result of the damage that solar radiation is doing to your retinas, so I don't recommend it. Duh. But when viewing an eclipse, the real concern is right after totality ends. During totality, it's dark, so your pupils have dilated to let more light in. But then there's the flash of sunlight when the moon moves off, and that's intense enough to damage your retinas. That's why astronomers recommend extreme caution when viewing an eclipse, because that flash can catch you by surprise. When viewing the sun, don't just stand there and stare at it. You should always have eye protection. And make sure you have safety-approved filters. Don't try the homemade tricks you might have heard of, like looking through an old CD or DVD or using old-style camera film as a filter. These can let through too much infrared and ultraviolet light, and again, can dilate your pupils, actually making things worse. Lots of companies make inexpensive filters that are great for sunspotting. We have links in the doobly-doo for more information on eye safety. Now, you don't have to worry about hurting your eyes at all when viewing a lunar eclipse, because in that case, it's the Earth that blocks the sun, and the Earth's shadow falls on the moon. So go nuts. But one big difference between the two kinds of eclipses is who can see them. A solar eclipse is localized to one spot on the Earth, or really a swath along the ground as the moon's umbral shadow sweeps across the Earth's surface. But a lunar eclipse is when the moon moves into Earth's shadow. So anyone on Earth facing the moon can see a lunar eclipse. This is why I've seen dozens of lunar eclipses, but never a total solar one. I've never been at the right place at the right time. Not that I'm there. The Earth has umbral and penumbral shadows too. When the moon first enters the Earth's penumbra, the dimming is so slight you hardly notice it. But as the moon moves deeper into the penumbra, it starts to darken. Sometimes it changes color, turning a deep orange or blood red. That's because the Earth is starting to block the sunlight heading toward the moon, and the only light that gets through is coming through the thickest part of our atmosphere. This blocks blue and green light, leaving only red to come through. That's why the moon and sun look red to us when they're on the horizon, rising and setting too. When you look upon the red eclipsed moon, you're seeing the light from all the sunrises and sunsets in the world hitting the moon and reflecting back to us. Finally, the moon starts to enter the Earth's umbra, and the real eclipse begins. At first, it looks like a bite is taken out of it. That curving arc is the shadow of the edge of the Earth. The moon moves deeper and deeper into the shadow until it's completely darkened. The Earth is bigger than the moon, so the Earth's umbra is much wider. While a solar eclipse is over in minutes, a total lunar eclipse can last nearly 2 hours. I once saw a lunar eclipse so deep that it took me a minute to find the moon in the sky. There's not a lot of new science you can do with a lunar eclipse, but if you know a little geometry, you can use the size and shape of the Earth's shadow on the moon to get the relative sizes of the Earth and moon. Ancient Greeks did just this and got a number that wasn't too far off. They also knew how big the Earth was using other methods, and so they had a decent estimate for the size of the moon nearly 2,000 years before the invention of the telescope. They also knew the shape of the Earth's shadow was always a circle, which only makes sense if the Earth were a sphere. If the Earth were flat, it would sometimes cast a thin shadow, but it never does. Pretty clever, those ancient Greeks. One final note. Because of tides from the Earth, which we'll learn more about in detail in a later episode, the moon is slowly moving away from the Earth by about 4 centimeters a year. As it recedes, it's slowly getting smaller in the sky. This means that eventually it will be too far away to completely cover the sun, and we won't get any more total eclipses. Doing the rough math, that will be in about 1 billion years. Better watch eclipses while you can. Today you learned that a solar eclipse is when the moon blocks the sun so its shadow falls on the Earth, and a lunar eclipse is when the Earth's shadow falls on the moon. We don't get them every 2 weeks because the moon's orbit is tilted, and if you're clever, you can use lunar eclipses to figure out how big the Earth and Moon are. This episode is brought to you by Squarespace. The latest version of their platform, Squarespace 7, has a completely redesigned interface, integrations with Getty Images and Google Apps, new templates, and a new feature called Cover Pages. Try Squarespace at squarespace.com and enter the code CRASHCOURSE at checkout for a special offer. Squarespace. Start here, go anywhere. Crash Course Astronomy is produced in association with PBS Digital Studios. Head on over to their channel and discover more awesome videos. This episode was written by me, Phil Plait. The script was edited by Blake DiCastino, and our consultant is Dr. Michelle Fowler. It was co-directed by Nicholas Jenkins and Michael Aranda, edited by Nicole Sweeney, and the graphics team is Thought Cafe.
Look at that bold styling. Not you. The Kia K4. Expansive interior space, and like that espresso, compact but packs a punch. Get great finance and lease offers today.
Kia, movement that inspires.
Shop your favorite brands for less during the Big Check event on Now at Sport Check.
Chuck?
Yes.
I'm excited about this one. I want to talk about the moon.
Okay.
There's a lot of these where we talk about the moon, but I'm going to put it all in one place at one time, here and now.
All right, that sounds good.
All right.
I will resist every
Chuck?
Yes.
I'm excited about this one. I want to talk about the moon.
Okay.
There's a lot of these where we talk about the moon, but I'm going to put it all in one place at one time, here and now.
All right, that sounds good.
All right.
I'm going to resist every...
moon joke, yes. Every mooning joke,
yes. Right now, I'm just putting myself in the mental space to stop thinking about butts and cracks and all of that.
All of that, moon, okay. Yes.
Here we go. All right, here we go.
All right, so this is mostly moon lore. I just want to put it all under one roof, okay?
Oh, I love it.
So let's start out with moon on horizon illusion. You ever hear about that?
The moon on the horizon illusion? No, I don't know.
All right, so what it is, it's what we call it, maybe you felt it. You see the moon rising over the city landscape or the mountains.
Of course.
And it's huge.
Yes, it's so beautiful. It's like a big, giant yellow ball.
Right. And you don't have that reaction when it's up overhead.
No, because it's a little yellow dot. And that's not impressive.
So why does the moon feel bigger on the horizon than high in the sky? It is not actually bigger at all.
Okay.
You can measure it. In fact, it's slightly smaller for other reasons I'm not going to get into. But it's completely psychological. And so we call it the moon on horizon illusion.
Nice.
Yeah, because your brain makes a judgment at all times how far away something is. It's making this judgment, okay?
Stereopsis.
Based on that, that's correct. And based on that judgment, it will say, here's how big I think that object is. Right, so think about it. If you look at, I'm giving a really stupid, obvious example. If you look up in the sky and you see an airplane, you're not saying to yourself, oh, the airplane's only this big, it can fit between my fingers. You're not saying that.
But you do take your fingers and hold it up and make it look like you're flying the airplane. Like, you know.
Yeah, I've never done that, Chuck. Yeah.
Okay. All right. Sorry, moving on. Moving on.
Sorry, I've never done that. So maybe others have. I don't know. I just personally, I don't believe I have to help the airplane through the sky. and I felt that way very early in my life. I didn't. So you know, not only intuitively, but your brain is doing subliminal calculations about how big something would actually be if it were right in front of you, for how small it is for how far away you see it to be. All right. So the moon, as far as your depth perception is concerned, is basically at infinity. Okay, it's basically at infinity.
That makes sense.
So what happens is the moon shows up in the company of terrestrial objects you are familiar with. Buildings, mountains, trees. You know how big those are. Okay?
Fascinating.
And then the moon is hanging out with them. And so your brain is like, wait a minute, is it really there? Or is it, no, but and while your brain is trying to figure this out, your brain starts thinking the moon is huge. Huger than at any other time in the sky. And by the way, you said the moon is yellow. You know why it's yellow when it's low on the horizon?
I mean, I can only guess that it's atmospheric.
Yeah, exactly. It's for the same reason the sun is yellow on the horizon. The sun isn't actually yellow. It's yellow on the horizon because the atmosphere is affecting the color. And if you have a polluted sky, it'll be deeper and deeper from yellow into amber and maybe even red. So you can get very sort of deep amber moon if it stays low. Point is, this is a moon on horizon illusion. And people say, I saw such a big moon last night. I'm saying, no, you didn't. You only thought it was big.
Wow. That is so cool, by the way.
All right, so now, last point about the moon on the horizon, okay? What's throwing off your depth cues is the full moon mixed in with other things that are familiar to you, as I've already said.
Correct, okay.
If you have the full moon rising over a horizon for which you have no depth cues, the effect is greatly diminished, and in fact, it's hardly there at all.
Oh.
For example, the moon rising at sea.
I was going to say, over the ocean.
Over the open ocean, there's no trees, there's no buildings, there's nothing. So that effect is greatly diminished. And you want to know how to get rid of the effect entirely? Here's what you do. There's the large moon on the horizon, next to the buildings and things. Turn around, okay? All right, with your back to the moon.
Okay.
Bend over and look at the moon upside down through your legs.
Okay, I got it.
Okay, now, don't pull down your drawers when you're doing this, because then you'll be mooning the moon, okay?
Okay, I got it.
Okay, now, don't pull down your drawers when you're doing this, because then you'll be mooning the moon, okay? But if you do this, then the buildings on the horizon and the trees are upside down. And your brain says, I don't know what that is. I don't know what upside down. I don't know what that is. Oh, so now I can put the moon where it belongs, at infinity, and the moon becomes its regular size.
So the lack of reference causes your brain to see the moon the way it is, instead of causing it to make the association to the size of the things surrounding it.
Correct. And and I invite you to do that experiment next time the moon looks suspiciously large on the horizon. Just bend over, bada bing, it goes right back to its size. Make it two bada bings in one.
Yes, you can. So what are you doing? Well, I'm looking at the moon and kissing my ass goodbye.
All right, so more about the moon. The moon is always opposite. The full moon is always opposite the sun. Right? That's why it's full. It's full frontal to the sun.
It's getting the full reflection of the sun.
The full reflection from our point of view on Earth. Okay. So, because you mentioned the moon is kind of yellowish on the horizon, yellowish amber, and I might have said this at another time, but here's a good place to reinsert it. All right. In the summertime, the sun it takes this very high arc across the sky. Okay. And then when the sun sets, it takes a very low arc beneath the horizon because it doesn't stay down there very long. Well, if it takes a low arc on the horizon, if you have full moon, the full moon will be opposite it and will also be in a low arc. Okay, so now watch. In the summertime, like in June, right? June, when the full moon rises, it stays low in the sky. Really low. It doesn't get very high at all. So if you had sort of sunset colors on the moon right when it rose, and it doesn't get very high, it's never going to free itself of the contaminating effects, the color contamination of the sky, of our atmosphere. So it'll come up, it'll be like deep amber, but it's not going to really ever not be amber in that very low arc across the sky. And then it sets, all right? Wait a minute. The full moon in June stays low on the sky, and it holds on to those sort of sunset amber colors. It takes on a kind of a honey color. Oh, of all the moons of the year, and they all have names, the name of the full moon in June is the honeymoon.
The honeymoon. What?
Bada bing.
That's sweet. Oh, I feel like I should be doing something more with the moon.
So I just wanted to bada bing the moon. Is that allowed? How many bada bings in a day do I get?
I don't know if you get the bada bing the moon, especially on the honeymoon.
On the honeymoon. So every moon every full moon has a name. You've heard of some, the harvest moon, this sort of thing.
Flower moon, the harvest.
And they're all cultural. and regional, by the way, depending on what mattered. There's a wolf moon, a snow moon, this sort of thing. So
the blood moon is my favorite.
No, don't go there, please. Don't.
Come on, man. Why not?
No, that's a whole other explainer. No, just that's a different explainer video. Back away from the term. Put the term down on the table and
Put
step
down
away.
the blood moon, sir. Sir, I'm going to ask you one last time. Put the blood moon down. All right.
Maybe I should. Should I slip it in here? Let me slip it out. We might run out of time. I don't know. Okay. All right. Do you know what the blood moon is?
I've heard of it. I don't know what it is.
But how are you talking about it? You don't know what it is, dude.
Because it's my favorite term for the moon, the blood moon.
So this is the term that some people invented to describe the full moon during a lunar eclipse.
Yes. That's where I heard it.
Okay, so a blood moon could then happen at any time of the year if there is a lunar eclipse. Okay, and what happens in a lunar eclipse? Earth interposes itself between the sun and the moon. Okay, so exactly interposes itself in such a way that
the moon is like, yo, hold me back, and the sun is like, you better hold him back because I'm about to mess him up bad. He's like, and
ladies and gentlemen, Chuck is from Philadelphia.
And the Earth is like, guys, come on, seriously, guys.
That's always what the person who's stopping the fight sounds like.
Why? Why is the person stopping the fight? Oh, wait, guys, come on, seriously.
It's never stop the fight. Right. No, the person sounds like that never stops fights. They start them. All right, so watch what happens. So we are in space. Earth is, people say, I want to go to space, just stand on Earth, you're in space. All right, so Earth is in space, and there's a shadow that's always there, cast by the sun. Okay, now you have the moon orbiting the Earth, and occasionally the moon will enter that shadow, blocking the light of the sun from the fully illuminated moon, and we have a lunar eclipse. Okay, so if you were to watch this from the moon, you'll see this dark orb move slowly and begin to blot out the sun. Okay, the Earth is much bigger than the sun on the sky. All right, so the sun is lost behind the Earth. Again, let's watch this from the moon now. Okay, so now here's what happens. Sunlight tries to get around to the other side by working its way through Earth's atmosphere.
Right.
Okay? So the light sort of disperses and refracts a little.
Almost like a filter.
But it's only around the edges because the full disk of the sun is blocked by the moon. Right. So it's just light that's trying to work its way around. If you have a heavily polluted atmosphere, then that sunlight gets deeply reddened as you have a deep red sun on a setting at sunset.
Right. Just like it would be on the horizon.
Just like it would be on the horizon. Okay, just like it would be, because the sun technically is on the horizon for that picture. All right, so if you have highly polluted or it's over the Sahara where there's a lot of dust particles kicked up, then it deeply reddens the sunlight that leaks around the Earth, and some of that spills into Earth's shadow. And so the moon, which would otherwise be completely blotted out, can take on a very deep sort of amber, ruddy, but okay, that can happen. I saw it happen several times in the 1960s and early 70s, and I've not seen that happen since. Ooh. We've been cleaning up the air of the Earth. Because what makes the sun deeply red, people say, oh, it's beautiful. Look, no, because the air got particles in it, okay? You're breathing pollutants, you're breathing particulates, all right? So that's what's reddening the sun. You have less of that, the sun is less red. In a lunar eclipse, I've not seen a red moon lunar eclipse in 40 years. Ooh. But they say blood red. Because it's not red, it's like a deep amber, all right? It's not any more red than someone who has red hair is actually red. No, it's just rusted color. Hold it to a red, is that red? No. Right. No, okay?
That's right, you little ginger kid, you.
Yeah, so what happens is people exaggerate the color of other people, right? All right? And so when they're being described, white people aren't purely white, black people aren't purely black. We have a word for how much light you reflect. It's called albedo, by the way. Albedo. So albedo of 1 means you reflect all the light. Albedo of 0 means you absorb all the light. But anyway, that's another explainer. We'll get to that. So that's my point. So that's how you would get a red moon. And people want to say blood. So I've seen people who are very taken by vocabulary, by words. Oh, blood red moon, that means something bad is going to happen. Just because somebody misnamed it doesn't mean you now have to take the word and create a whole system of cultism around the word that someone badly chose to describe an object in the sky.
Well, thank you for making me hate blood moons now. It went from my favorite to the worst.
I'll just say, so what happens is the moon gets eclipsed and just basically disappears from the sky. In fact, most people who've ever witnessed a lunar eclipse didn't even know. Because it looks like you have a crescent moon. The Earth's shadow is curved, and it just looks like a crescent moon. And it gets a little dimmer, and then it just disappears completely. And then you don't even notice it until it sort of reemerges on the other side. So a lunar eclipse is long and boring and hardly noticed by anybody who isn't looking for it. It's just a reality check. Don't shoot the messenger. All right.
And it speaks so highly of you.
Chuck, did I explain you out? Did you got any?
I don't know, but I know we're out of time.
Yeah, we're out of time.
Yeah, that was good.
We're out of time. So until next time, I'm Neil deGrasse Tyson. People think.
Leo's working hard, growing. Pampers is working hard, keeping him dry. Only Pampers Swaddlers has a Keep Dry liner to keep him comfortably dry. Pampers, behind every baby.
Every great love story comes with a promise. The Hyundai Elantra comes with the best-in-class new car warranty that's there for you when it matters.
Yes.
Is that time again?
Yes, it is.
Are you ready? Can you handle the truth? Can you?
No, I can never handle the truth. That is why I lie to myself all the time. My life is a web of lies, and I like it like that.
I occasionally get questions about the naming of things in my field. All right, and let's take, for example, the names of the moon, of planets and their moons. All right, had you ever wondered how we get these names?
Not really, but I mean, I figured somebody looked up and said, I'm going to call it that. Because
somebody did it.
Right, because for me, it would have been like, Jupiter, and then Jupiter A, B, C, D, Jupiter 1, Jupiter 2, Jupiter,
That's because you have no imagination, right?
Well, that goes
so here we go. So the planets are named, they all have Roman, Latin names, basically, okay? And so they named after sort of Roman gods. You have Mercury, the messenger god. Mercury's the fastest moving planet. Venus is quite beautiful in the evening sky. That object got named for Venus, the goddess of love and beauty. And then also in the sky of Mars, which is red, the color of blood. So the warrior god got named after that planet. Or that planet got named after the warrior god. And let's keep going. You have Jupiter, Saturn, and those are the planets known to the ancients. And then later would be discovered Neptune, Uranus and Neptune. Right. And the thing about Uranus was it was the first time anyone discovered a planet. It was William Herschel back in the 1700s. And it was like all the other planets were just known because they're just in the sky. There's not the person who discovered them. Anyone who looked up noticed them. So no one's on record for discovering Mercury, Venus, Mars, Jupiter, or Saturn. But Uranus got discovered. And it got discovered by William Herschel. And no one had discovered, and therefore no one had actually named a planet in modern times.
Wow, he picked a good one.
He tried to figure out what to name it. And so he did the right thing. Okay, he named it after his principal funder. That's what scientists do.
Wow.
Artists do the same thing. They draw in the background the benefactor or whatever, the sponsor of the painting. That makes the rich folks feel good.
Right.
So he named this new star after King George.
Okay. All right.
No, that's the King George that's of the American Revolution. That same King George, because this is the late 1700s, and so that's the same George that John Hancock signed his big signature large enough for him to read.
The same George in Hamilton.
That same George. That's correct. That same King George. So,
by the way, that King George, God, he was a show stealer.
He was good. So I have books from that period, so late 1700s, early 1800s, where the enumeration of planets is very clear. We know Earth is a planet, right? So Mercury, Venus, Earth. Since Copernicus, we knew that Earth is a planet as an object that goes around the sun. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn.
George.
And George.
Of course.
And George.
Right.
I have books that list the planets in that order with those names. And this was, you look back and say, what? You know? And so
God, we should have left that. I'm telling you right now, that would be the best thing in the world. One day, we are going to get to George.
With our greatest of technology.
With our greatest of technology. We shall one day set foot upon George.
So
we could have, instead of Uranus, Uranus, we could have went with George's ass. Planet George's ass.
You're going to say it with a British accent, right?
Exactly. Planet George's ass. I'm so terribly sorry. I say, one day we shall get to George's arse.
I say.
Oh boy, one day we'll get there. So looking forward to being firmly planted in George's ass.
Okay, stop. That's enough.
Okay. Oh no.
Okay, so it would take a little while, but clearer heads would prevail. And how do you tell the discoverer of a planet that he has to unname it after his king? This is very tentative, diplomatic moments here. And so finally, we landed on Uranus, which, from what I have read, is similarly pronounced in both Greek and Latin, in Roman. It's the same word, all right? So it's actually a crossover name between the Roman and the Greek. Okay,
that's cool.
So that'll show up later in a minute. So and after that, we get to Neptune. There's a Roman god of the seas and this sort of thing. And then when Pluto was discovered, when everyone believed it was a planet, Pluto is the god of the underworld, and it's Roman. So there you have it. All right. So you might say, well, what about the Greeks? In the Western traditions, they were pretty significant in what they contributed to all of this. It's not just the Romans.
Right.
Romans are like Johnny-come-lately compared to the Greeks. Yeah. And so we said, okay, in our Western astronomical traditions, we will honor not only the Romans with planet names, we will honor the Greeks with moon names.
Aha.
Okay.
There we go.
So all moons, essentially, there's some exceptions here I can get to. All moons in the solar system are named after Greek characters in the life of the Greek counterpart to the Roman god after whom the planet is named.
Gotcha.
Are you with me on that?
I'm with you on that. So basically, you take the Roman, all right, you find a god, and then you say, okay, how's that translate into a Greek god? And now we got a name for a moon.
No.
Right.
No. You got almost all of it.
Almost.
So you got the Roman god.
Right.
Ask, what is the Greek god counterpart to that Roman god? Okay. Now you look at characters in the life of the Greek god.
Gotcha. So
and those are the names of the moons.
Right, because otherwise you would end up with just two gods.
Two gods
on different sides of the coin. Right.
Yeah, but one would be a planet, one would be a moon. That wouldn't be right.
That wouldn't be right.
You'd be pissing off some powerful god.
Yes,
so let me give you a list of some of these moons.
Okay.
Mercury doesn't have any moons, and neither does Venus. Okay. And let's skip over Earth for a moment. We'll get back to Earth. So what's next? Mars. Mars has two moons, and they're pretty sorry moons. They're like a dozen miles across. They're not even spherical. They're embarrassments, basically.
They really are.
Yeah, people wondering whether they're just captured asteroids.
I was going to say, that sounds like a rock. That doesn't really sound like a moon. It sounds like a rock that got lost.
Yeah. A wayward rock.
A wayward rock.
Somebody lost their rocks.
Exactly.
So the Martian moons are called Phobos and Deimos.
Phobos and Deimos.
Yes, Phobos and Deimos, as I have read in the Greek tradition. That's the name of each of the two horses that drives the chariot of Mars across the sky.
I got you. Phobos and Deimos.
Yes.
Which, by the way, Deimos is a really cool name. So,
Deimos, yeah. It totally is.
Wasted on a rock, I got to tell you.
It is.
As cool of a name as Deimos is, you wasted it on a rock.
Yeah, it looks like Idaho potato. It's embarrassing. But it's all it's got. So, in fact, one of the Mars rovers, I forgot which, was in the path of a Phobos or Deimos, Phobos eclipse, right? So it's got a picture of Phobos passing in front of the sun, and it's just this outline of Idaho potato deep within the full disk of the sun. It's embarrassing.
Yeah, that is.
It was like, it couldn't even cover the whole sun because it's so little, and it's not even round. So anyway, let's keep going. So it comes after Mars. We get to Jupiter.
Uh-huh.
So Jupiter, its 4 brightest moons were named, they're called the Galilean moons. Galileo first saw them through his telescope and then described them. But this is, let me remember, we have Io, Ganymede, Callisto, and I forgot one. Callisto, Ganymede, Io, and...
Don't look at me. I hope you're not helping me.
Help a brother out.
Yeah. You're not waiting for me to jump in. Once you got past Ganymede, I was just like, oh, shoot.
How could I forget Europa? My gosh.
Right,
Which was the star of the movie 2010. So, Io, Callisto, Ganymede, and Europa. Those are the 4 biggest moons of Jupiter's. I lost count. Is probably near somewhere around 100 moons or more. Because every time we get closer to it, we see other tiny little rocks. And what distinguishes a moon from just like a not moon? You know, if it's orbiting and it's bigger than a dust particle, is it a moon? Can you be a moon no matter how little you are? This is a debate, and I'm not going to bring that up here. But I'm just going to say those are the 4 big ones, and those are the ones that kind of really matter. When you see Jupiter through a telescope, there they are. Okay,
nice.
And it's 4 of them. They go around Jupiter. And Galileo, when he first saw them, he said, "Oh, they're stars near Jupiter." And then he looked later on and he said, "Wait, the stars have moved." He called them the Jupiter stars, right? And because why would you think you're discovering a moon? This isn't. You're coming out of nowhere and landing on this information. And so he was able to see that they moved around. They orbited Jupiter. Oh my gosh. That meant that Earth was not the center of all motion.
Look at that, yeah.
This was devastating to people who wished it were otherwise.
And the Jupiter Stars sounds like a really bad basketball team.
The Jupiter Stars.
It really does.
It's a bad any kind of team, right?
Yes, exactly.
Bad soccer team.
Right.
So now let me take you to Uranus.
Right.
Okay? There was a pact so as not to piss off the Brits, who were very powerful in the late 1700s. Okay? All right? They're one of the most powerful forces the world had ever seen, particularly with their naval power. Okay? So, you're going to piss off the Brits and King George? What are you going to do? So here's what they did. We said, okay, we will make an exception of the Greek rule for the planet Uranus. And we will name the moons of Uranus after fictional characters in the plays of Shakespeare.
Oh, okay. I have never heard this.
So this threw a bone back to the Brits, so that they could rest easily that their king was stripped from the name of the planet, and it became a Roman god.
Wait a minute. A constellation prize.
Oh
God.
Chuck, that was good. Chuck, that was good.
I say about it.
I gotta hand it to you. So, what are some names? We have Portia, P-O-R-T-I-A. Remember Portia from your Shakespeare?
Okay.
There are a lot of characters from A Midsummer's Night's Dream, because that's quite a fantastical storytelling going on there. Among the moon names, we have Umbriel, okay, Titania, Miranda. Miranda's the lead character in The Tempest. We have Ariel, Oberon, so Puck, Desdemona. All these moons have names drawn from Shakespeare.
No, that is really stunning, because I can't believe that's just something that everybody should know, because it's so it feels so random.
Well, it's a little bit of history. It's fun history. It's not science so much as it is just it's the intersection of science taking place embedded in our culture.
Yeah. Yeah.
So now you go out to the outer planets. By the way, Pluto, the first moon was discovered around Pluto. It was named Charon, I think in the Greek is Charon. And Charon is the ferry boat driver who carries your soul across the river Styx to Hades.
Makes sense. Pluto got of the underworld.
Well, yeah, so it's Hades. That's so you go to the Greek side of that. So make a long story short. So this is the origin stories of the names of the moons. And in the very later years, when there are many more moons discovered and you run out of incidental characters in the life of Greek and Roman gods. By the way, we had many because they led complex and interesting social lives, right? So there's a lot of characters you could draw from. But in modern times, a more inclusive sensibility has descended upon us. And so now there are names of gods and other spiritual beings, fictional beings from other cultures, not just Greek and Roman. When we fully flesh out all the names of all the moons. So that's Solar System Moons 101, Chuck.
Oh man, I'm telling you, that was really cool. However, from now on, I'm sorry, I have to call Uranus George's ass. That's it.
There you go, Chuck. We got to call quits there.
Okay.
All right. Great. Another Star Talk explainer. Just blowing Chuck's mind. That's what I live for, Chuck.
Good. I'm always glad it happens.
And the first mission to land on Uranus.
That's it.
We will name features of Uranus George's ass. I'll strive to make that happen. All right. Star Talk explainers. Keep looking up.
How it feels to chew 5 gum. senses.
Tide Free and Gentle. It's free of dyes and perfumes. It's gentle and effective.
This is Dalton. Hey, Dr. Tyson, Lord Nice Greetings from Huntsville, Alabama. I was watching
Rocket City.
Rocket City.
Which Trump officially named. Well, but it was always named Rocket City, right? And then Trump decided to.
I'm going to officially name it Rocket City, not to be confused with Little Rocket Man.
Just like coming to New York, I'm going to rename New York the Big Apple.
Which he would do that, by the way. Anyway, that's so funny. Greetings from Huntsville, Alabama. I was watching an old explainer on absolute zero and why it's impossible to reach it. It is impossible by quantum physics to have a particle become completely stationary. Then would it not be possible to extract infinite energy from it in the form of heat? In doing so, violating the first and second laws of thermodynamics, it seems a bit paradoxical to never be able to reach absolute zero, since you seemingly can always have something colder. But that I don't know why you would say you seemingly could have something colder.
No, it's a. He's what this is Dalton. He's merging a classical brain with a quantum brain. Okay, right. In terms of his interest in answering the question.
Right.
So just let me talk you through this.
All right. Talk off the ledge, Dalton. It's gonna be okay.
Talk you off the absolute zero ledge.
Yeah.
All right. So let me just remind people that there's no such thing as cold.
Right.
You can't put cold in something.
That's where I was going when I said it's.
If you could do that,
right,
then you can make something like infinitely cold.
Yes.
Just add more cold. So what we sense as cold is just the absence of heat.
Right.
So you start pulling heat out.
Right.
This is what your refrigerator does.
Right.
It pulls heat out of your food.
Right.
You don't think of it that way.
Right.
You put in something that's room temperature. It takes the heat out.
Right.
If you take heat out of something, what happens to its temperature?
It goes down.
And you take it out. Where does that heat go?
It's got to go somewhere.
You ever go around back of the refrigerator? You ever go around back? You ever go around back? Those coils are dissipating coils to send out the heat. It not only radiates the heat, but it's in touch with air, so the air will conduct heat away as well.
Right.
Okay. But it's a major issue with spacecraft.
Okay.
Because if you're in space and you have machines that generate heat,
right,
how do you get rid of the heat? You got to dump the heat somehow.
Okay.
So you can't just have well, you can have radiators, yes, but each radiator has to be pointing away into space.
Mm-hmm.
They can't point to each other. You can have a battery of radiators, right? Not a little battery, but like
an array
of radiators. That are, like, they point to each other. Right. Nothing. It just feeds each other the same heat.
Like, I'll heat you. You keep
exactly. So they all have to face space, but it doesn't have the benefit of air whisking away the heat. It can only radiate it away. Whereas on Earth, you can release heat both ways. Okay. You can radiate away, and you can convect air around it, and it just takes it away. Right. Very efficient.
Right.
When you have a medium such as an atmosphere to do that. Right. So
cool breeze.
The cool breeze will cool you down faster than just you radiating your heat. Okay.
Right.
It's slightly different. The cool breeze is forcing your sweat to evaporate, and the evaporation takes energy out of you. But so let's get back to the absolute zero. So I keep taking heat out, and the temperature gets lower and lower and lower. You reach a point where quantum phenomena dominates, and you can no longer use classical reasoning. This, by the way, Dalton's not alone in this. Intersection, this troubled paradoxical intersection between classical physics and what we call modern physics. Okay. So you get down there and you try to take more heat out, and you can't because and by the way, taking heat out means that particles are moving slower and
Slower,
slower.
right.
Okay? The heat is vibrational energy typically. Okay, so you take that out, and there's a regime where the quantum fluctuations prevent it from ever stopping its motion. Right?
Okay.
So you're saying, that means there's energy there.
Right.
Let me pull that energy out.
Let me utilize that energy.
I think I'd have to confirm this with our cosmology trio.
Brian and Jana.
Brian Cox, Brian Green, and Brian Cox, of course, is in the UK.
Right.
But he comes through. He's a good friend.
And then sometimes Sean.
Sean Carroll.
Right.
Oh, yeah, he's a good guy, too. When we speak of 0 point energy of the vacuum of space,
right.
I think that's what they're referring to. The energy below which you cannot go, because it's 0 point, but it's not really zero.
Right.
But if you try to get to zero, that's what you're stuck with. And that's quantum fluctuations. And I don't think you can extract energy out of that lowest energy fluctuation, because to take energy out, you need a lower energy state to land in.
Right.
And you can't.
Right, because that's it.
Who was the guest we had in another show? A biologist who said the universe is just electrons looking for a place to rest.
That's it. Yeah, that was Bitul.
Bitul. Yeah, Bitul from University of Madison, Wisconsin.
Yes.
Bitul. The universe. Everything that happens in the universe is an electron
looking for a place to rest.
Looking to hang its hat.
Yeah.
And so...
Honey, I'm home.
A hard day in the circuit. So yeah, but people imagine that you could tap the 0 point energy and make like rockets out of it and travel through space. And I don't have problems with people imagining that. It doesn't seem likely to me though, based on what we know of the behavior of quantum physics.
Gotcha.
So they have.
All right, Dalton, way to go, brother. I hope that keeps you from
keep you on the ledge.
Jumping off the ledge. All right, this is Rachel Ambrose. Rachel says, Rachel here from Austin, Texas. Photons have to be literally everywhere all the time, even in a dark room. If I can see, then there's photons hitting my eyeballs. I feel like people don't talk about this enough. They are filling every inch of space all the time. They're everywhere. Furthermore, somehow photons from the Big Bang are still here right now in the form of cosmic microwave background radiation. Neil, can you please speak to this?
Yes. Muhammad Ali said it best.
Mm-hmm.
Okay?
I'm pretty. That's right, Howard. Look at me. I'm pretty, Howard.
Howard Cosell.
Howard Cosell. I'm so fast. I'm so fast. I turn off the lights and I'm in bed before the room gets dark.
That's the one I'm talking about.
Yeah.
That's the one I'm talking about.
Yeah.
So he knows that photons have to go,
right.
Well, he's thinking the dark is penetrating the room,
right.
but light is exiting the room. When you turn off the light, the light gets absorbed and it's gone. Your eyes are not the ultimate arbiter of whether there are photons in the room.
Right.
Because your eyes only see red, orange, yellow, green, blue, violet.
Right. Biv.
Also indigo, violet.
Indigo, violet.
You gotta get the Biv going there.
Yeah.
You know, Isaac Newton put in the eye?
Did he?
Yeah. Because he's mystically fascinated by the number 7. The spectrum can't have 6 colors.
Can't have 6 colors.
You gotta,
yeah. Kind of animals do have 6 colors.
What a stupid universe would that be?
Yeah, throw some indigo in there. Yeah.
No, but if he got deeply religious, he could say, well, the universe was created in 6 days.
Right.
You know, not 7 days, 6 days.
Yeah,
People forget it was 6 days.
7 days he rested.
He rested.
Which I'm just saying, what kind of God is this?
He needs to take a break.
God, me is so damn hard. Oh, me is hard.
Oh, me. Oh, my me.
Oh, my me. It's so hard to make a universe. I need a rest. Oh, Lord, I can't do no more. Did I say, Lord, who am I talking to? Oh, Lord, me is hot. It is. Oh, I'm so tired. Anyway, okay.
So, but now I forgot what we were talking about.
Photons everywhere.
Right. So anything that is at any temperature at all is radiating photons.
There you go. That's what I was going to say. Because if you're a predator, you see photons all the time.
You mean the movie character?
Yeah, the monster with the dreadlocks.
Yeah, because he had dreads.
Yeah.
He had dreadlocks.
Yeah.
So Predator could see in infrared.
Right.
Okay.
Exactly.
Now, you know what's interesting?
Ahead.
There's a little fact.
Right.
I think about movies all the time.
Okay.
So that was only cool because the infrared was the shadowy shape.
Right.
That means he has low resolution infrared camera.
Right. Yeah.
We got better cameras than that today.
We do.
High resolution, you see the full person there. Depending on your temperature, it will determine what kind of light you're predominantly going to emit.
Right.
So at our temperature, we emit primarily infrared, so we'll show up in infrared. We reflect visible light, but we emit
infrared.
Your walls are room temperature, so they'll emit a little less infrared because they're not as warm as we are.
Right.
You keep dropping the temperature. What's on the other side of infrared? Microwaves.
Okay.
And then radio waves. So the colder it is, the further down the spectrum it shifts. So that when you're only 3 degrees Kelvin, 3 degrees above absolute, you're giving off microwaves.
That's it.
And that's the cosmic microwave background.
Space, right.
That's it.
Cosmic microwave background.
So yeah, and it can be dark for you, no problem. Not many people have been in complete total darkness in their life.
True.
Do you know how to get it?
I'm going to say blindfold and then bury yourself alive.
I was thinking of other ways for that. But if you go spelunking.
Oh, you mean to a cave?
Into a cave. You go deep into a cave,
right.
but if you turn,
so there's no light
and
in at all.
Turn off your flashlight,
right.
You cannot see anything.
Yeah. See, now, and no disrespect to anybody, but that's some white people stuff.
No black man ever died.
You will never find a black man dead in a cave with no light at all. First of all, I'm not going in there because even with a flashlight, be like, Rich, no, I'm not doing it. I'm not doing it, okay? These are jokes. Don't write. All right, I'm going to stop. Let's move on. All right, so there you go. Rachel.
Yeah, so, but I like the Muhammad, give me the Muhammad Ali comment.
That's right. I'm so fast. I turn off the light. I'm in the bed before the room gets dark.
Yeah, that's good. That's a really good one.
As a parent, you enjoy a relaxing and quiet ride. The new Kia Carnival can certainly help.
Kia, movement that inspires.
This is Max Wilburn, who says, hey, Chuck, hey, Neil, this is Maxwell from Lexington, Kentucky.
Ooh.
And I know Neil thinks very highly of Newton, as he has accomplished so much, but recently I learned about Newton's law of cooling. Although it's not as fundamental and such a stepping stone for the world of physics, I just find it insane that as a side quest, this is Max Wilburn, who says, hey, Chuck, hey, Neil, this is Maxwell from Lexington, Kentucky.
Ooh.
And I know Neil thinks very highly of Newton, as he has accomplished so much, but recently I learned about Newton's law of cooling. Although it's not as fundamental and such a stepping stone for the world of physics, I just find it insane that as a side quest, he did that. What a badass. What are your thoughts?
I did not know about his law of cooling.
I think his law of cooling was, don't you love my hair? Look how cool it is.
But I think that was the wig he was wearing.
Oh, no.
I was so distraught upon learning this.
Really?
Yes.
So his hair notwithstanding, do you have anything to say about the law of cooling?
So I didn't know he came up with that, but it is a well-known means of calculating the rate of temperature change in physics class.
Okay.
Yeah. So the way you do it is you have two materials at different temperatures.
All right.
Okay. And you bring them in contact in some way, either physically, so atoms are touching each other, or have air molecules bouncing back and forth. Temperatures.
All right.
Okay. And you bring them in contact in some way, either physically, so atoms are touching each other, or have air molecules bouncing back and forth, or they're radiatively connected. Connect them in some way.
Okay.
Okay. And then you measure the rate at which the temperature changes so that they reach equilibrium to each other.
Cool.
Okay.
Right.
So it's not just that sorry. One of them might have a continual source of energy going in.
Mm-hmm.
So then the cool thing comes up to its temperature. You see what I'm saying? But if they're two isolated objects at different temperatures, they will meet in the middle somewhere.
Right.
At a temperature lower than the high one and higher than the low one.
Gotcha.
All right. So you can calculate the rate at which the temperature changes.
Oh, okay.
Okay. And deduce, as Isaac Newton apparently did. I own everything that man's ever written, and I got to go dig that up.
Cool.
That must be a chapter I missed.
Yeah.
Okay. So what it states is the bigger the temperature difference, the faster the rate of change of temperature will be.
Okay.
Which kind of makes sense. It just kind of makes sense.
Absolutely.
Yes.
Right.
And if you do some measurements of that, you can actually represent it with an equation.
Okay.
And you make a prediction.
Right.
This is the temperature difference. They'll be the same temperature in 10 minutes.
Right.
Or, by the way, this is happening every day. You get a glass of water, you put ice in it.
Right.
Eventually,
it's going to be water.
The ice will melt. And then you have water that's cold, but it's still air temperature out here.
That's right.
Eventually that comes up.
And that was an assignment in physics class when I was in 8th grade. And what we had to do was plot the melting of the ice in a graph to see whether or not it was linear. And it was.
Yeah, that would be a cooling curve.
Yeah, that's
because it's gaining heat from the outside.
Exactly. Yeah.
So
there you go. Look at that. See, people, these are the things you can think of when you are not busy thinking about sex. Like Isaac Newton. This is what happens when you become a genius. Because he's just like, well, I ain't having sex, so I might as well think about how the things melt.
Yeah, he never married, had no children, had no known intimate relationships. And so we're pretty sure when he came up with his law of gravitation and motion and calculus, that he was a virgin.
Right. There you go, babe. That's it. Like a prize fighter. You know what I mean? You know what they say? You gotta stay hungry. All right, here we go. Ben Brunn says, hey, Star Talk, this is God, here to bestow upon you the keys of limitless energy.
Ooh.
What do you do?
Oh, well, first, I don't think it requires God. we just have to tap the energy from the sun.
There you go, bro. We got that. Nice.
God, we'll worry about somebody else. Take care of a homeless man in the street. We got the energy thing. We're kind of slow on the go here, but the sun has basically unlimited energy. And the Chinese are now going to put up a solar array in orbit, where there's no clouds. And if it's far enough away from Earth, it always sees the sun 24/7. Beam it down to Earth by microwaves. So then you have this column of microwaves. What could go wrong?
I'm going to cross that path for sure.
But unlimited energy. Here's what I would do. You ready? I would do what they did in Iceland.
What's that?
Iceland is sitting on top of volcanoes. You know this?
Yeah.
Okay. So it's volcano land. It's not Iceland.
It's not Iceland, yeah.
Greenland is Iceland, not Greenland.
Right, exactly.
All right. It's the opposite here. So I would do what they do in Iceland.
Go ahead.
They heat their water at these lava pits up in the mountains and then send the water into town, but they do it under the streets so that snow never accumulates.
Genius.
You don't need snow plows. You don't need salt. Right. You don't need accident reports.
Nope. It snows and then the streets they're just clear.
I would run hot water under everything. And then you just snow be damned.
It's a radiant heating for your whole city.
Yes.
Wow, that's cool.
Yes, and other things I might use unlimited energy for.
I'll tell you what I'd use it for. Pretty much shutting down every war that's ever been fought. Because most of these wars that we fight are over some form of energy. You know, right. And so it's just like, well, guess what? It's unlimited, guys. What are you fighting over?
Well, it can also be over food or water supplies. There are other costs.
There are other scarcity resources.
Right. I think you'd be smart enough.
But with unlimited energy, you would need water.
Today, nobody's going hungry because there's not enough food in the world.
Exactly.
If you're going hungry, it's because
some greedy bastard is keeping you from food.
Disrupting the food chain.
Exactly.
So I don't think that was predicted back in 1900.
No, right.
We saw the population growing exponentially, and we saw the food supplies growing linearly.
Yes.
And
there was a point where people thought that we would run out of food.
And just completely starve.
Right.
And so run out of food to feed everyone.
Right.
Well,
rich people always want to eat.
Right.
Exactly. Yeah. Wow, so that's cool, man. I love the idea of radiant heating for your city, though.
Yeah, just so you don't have to do it.
Yeah, especially since we got 2 feet of snow. All right, I love that answer.
You know we can see you, right?
Teens might not care if you protect your home, but we do. Claims-free homeowners save more with TD Insurance. It's how we're making insurance more human.
Because after Chernobyl and after 3 Mile Island and after Fukushima, nukes just left a bad taste in people's mouths. It was always that way, and these then just became evidence for it. And so there's a lot of rebranding that's going to have to happen going forward if nuclear energy is going to rejoin the conversation. So what are your challenges squaring that circle from the sources of energy people typically talk about, especially in the green movement, and nuclear energy as a kind of wannabe as part of that conversation?
Yeah, absolutely. I think a lot of it's around numerics, right? Talking to people about the metrics that matter. If you're worried about safety, the metric that matters is deaths per terawatt hour generated.
You have that? That's a statistic you guys have?
Can I just say,
absolutely.
can I just say I'd be very concerned about that statistic, the death part? Yes.
That's just weird to count deaths by how much electricity has been produced.
Nuclear energy. You'll only die once in a while.
No, but does that exist for coal?
Yeah, it's only interesting as a metric if you're using it to compare energy sources. And so a number of different data sets have informed a number of deaths per terawatt hour from solar, wind, coal, etc. And nuclear is way, way, way down at the bottom. You're slightly below solar and wind, actually, even if you include Fukushima and Chernobyl, interestingly, deaths at 3 Mile Island. And you have geothermal, I think, is one of the only ones that is lower than nuclear in terms of deaths per terawatt hour. And it's construction projects. There's serious issues maintaining wind turbines, like putting things on roofs and installing. That sort of thing doesn't happen on a nuclear construction site because of the incredible amount of regulation. And so you really are left with accidents. And so there's plenty of life cycle analyses of deaths, but also carbon per terawatt hour. And the reality is nuclear, in terms of generation, is higher, and so the denominator is huge.
But higher as a return, it's higher.
There's more power generated
per anything.
So the terawatt hours are higher.
Yes.
By a long shot.
Yes. Oh, so that's how it wins. I get it. If you have gerbils on a treadmill producing your energy, and it kills 1,000 gerbils, they didn't make much energy to begin with, right? So the death rate relative to the energy return, that ratio is bad for you. Again, correct me if I'm wrong, Kevin. Nukes are so potent in the capacity to produce energy that whoever died doing whatever, there's so much energy produced at the other end, it compensates for that.
It's a relative number.
It's a relative, correct.
Doesn't it beg for more regulation in sort of renewables? Like, you're right about solar. Like, some guy that was working at Jiffy Lube is now selling you solar panels and putting it up half drunk. Like,
that sounds like a bad experience on your behalf.
We call him my uncle.
That's way too precise an example.
My Uncle Archie. Just anything, but doesn't it sort of beg for that on some level, sort of, if there's that level of sort of death rate relative to renewables?
So interestingly, renewables like wind and solar and geothermal nuclear, they're all in the same category, which is just magnitudes and magnitudes lower than fossils. And nuclear ends up winning because historically nuclear has been the largest source of carbon-free, emissions-free power, right? And it's those emissions from the fossils, and that really takes them to a completely different order of magnitude in terms of deaths per terawatt hour. And so I would say that renewables are safe.
So, this is it.
This is a quantum computer.
This is a quantum computer. Here I am seeing a real-life quantum computer for the very first time with my friend and king of tech YouTube, Marquez Brownlee. And I'm finally understanding why quantum computers are such a big deal.
Quantum computer. Quantum technology. What on earth is a quantum computer?
It's qubits. Try all the codes at once.
Whichever nation first develops a practical quantum computer will have a tremendous advantage.
Quantum supremacy. I see a lot of news about quantum computers, and it's always extremely confusing.
That was really well done, and I still need to rehear.
But also, it's often wrong. Quantum computers aren't supercomputers. They aren't bigger, faster versions of what we use now. There's something totally different. And that difference is actually the key to understanding why they're such a big deal. Why governments around the world are battling it out to build them the fastest. Quantum computers are wild. They're on track to change what we can build and how we understand the world. They're kept at temperatures colder than space. But if you think you really understand how they work, you're probably wrong. At least I didn't. And that's where this video starts. Marquez and I both realized that there was this big, important technology that we really didn't understand. So we decided to go on an adventure to figure out the truth about quantum computers, what they can really do, and why we should care. And of course, we're taking you on that adventure with us to show you what we learn as we learn it. And more importantly, to show you how these crazy computers may actually impact your life, and sooner than you think.
It's a very niche skill we just got, which is being able to hear when a quantum computer is working.
What does it sound like?
So it works. It's not broken. I swear I'm usually good with tech, but...
Like, the only function of this screen is to provide directions. You're getting it? So we're going to visit IBM's quantum computer. This is really exciting that they're letting us see this computer because it is, to my knowledge, the largest quantum computer that exists, which I say with confidence, like I know what that means.
I was gonna say, what is biggest? Because like I heard, you know, like supercomputers, they're massive rooms full of computers, and when someone says they have the biggest supercomputer, I'm like, oh, I can picture that. The largest quantum computer, I'm not even sure what to picture.
I imagine the golden octopus. You know that thing that Biden looked at like this?
The press images, yeah.
And I know that in order to see that, they have to shut down the computer. So this is like, took some real logistics on their part to allow us to see it.
A real deal.
What is most interesting to you about quantum computing?
It's definitely on the edge of my expertise, I would say. I'm really curious about when it's actually going to touch like regular people. My whole concern is purchase decisions. At some point in the future, quantum computing will come into play with a real purchase decision. Someone will have like a device that they can buy where quantum computing is a part of it, or maybe went into its creation at least. When are we going to get to that point?
One of the things that I think is very important to make clear is this is a different kind of explainer. You're just coming with us as we figure this out.
Exploratory explainer.
Exactly,
yeah.
The whole new genre. Along with this adventure are Cody and Nicole. Nicole is an associate producer on this episode who is also studying quantum communication for her PhD. And Cody is our DP, the man behind the camera. Thank God they're both here. So, when I started doing this episode, I spoke to a really famous quantum physicist. He was really frustrated at the way that people were talking about quantum computers. And I was like, okay, how do you want people to think about that like that? Okay, here's the analogy that helps me understand what quantum computers are good for. Imagine that you're on a video game map, and how you get around depends on how good you are at doing math. You may not want to play this video game. Bear with me. So first, there were no computers. Things like geometry and astronomy took forever. So you have your little pencil and paper, and you're traveling across the mathematical map by walking. So it was slow. And there were lots of areas that we just couldn't explore because it was beyond our computational ability. But then we developed early computers, and that allowed us to input larger data sets and answer problems that had previously been out of reach. These new computers unlocked new areas on our mathematical map. Instead of walking everywhere, we can now ride horses. We can get farther, faster, and we can access areas that were previously inaccessible. But there were still parts of the map that our computers couldn't access. Luckily, computers just kept getting better, and they allowed us to solve more and more complex math problems. As a result, our virtual map has transformed. We have roads and cars, and we're just reaching areas that were previously unreachable. Better computers mean traveling across this map faster and more easily than ever. The thing that was really important to understand is that quantum computers are not faster cars, they're boats. A boat is not necessarily better than a car. They're just built for totally different terrain. So with our new quantum computers, we're beginning to navigate these new mathematical waters, solving problems and discovering areas that traditional computers just can't. My question for IBM is, what's in the water? Like, wow. What are the oceans that we're all of a sudden able to explore with our quantum computer boats?
I love this. I'm an analogy person, so I'm like fully absorbed in this now.
This is why I think a quantum computer is never going to beat an iPhone. But I think that this is a better thing to offer the audience, like to offer you guys, instead of like quantum computers are just another exciting computer.
I guess what people are probably clicking on this video thinking in their head is, will there really never ever be a quantum computer in my pocket? And I guess that would be, will there ever be a flying car boat? You know, is the tech ever going to get to that point? Just a question.
I just want to say I really appreciate your commitment.
I love it. I love the analogy.
Guys, we have arrived. Where we have arrived to, this does not look like there's a quantum computer here. IBM Research Division. Here we go. All right. Let's go. Let's see a quantum computer. We made it.
We're here.
Here we go. Do you want to introduce yourself first? Oh, sure. Olivia, audience, Olivia.
Hi, I'm Olivia Lanes. I'm a researcher at IBM, and I also work on the education and the community team. We're going to go look for a quantum computer. What's going on here? This is our Watson setup. No, please go ahead. This is like where the Watson AI thing was displayed, and it like competed on Jeopardy with like Ken Jennings.
Watson, what is you? You are right.
This is Brent. It's Brent's lab, so it's very nice of him to
Great to meet you. Thanks for having us.
So this is the lab.
That's a quantum computer?
Yeah, actually this is a dilution refrigerator. This whole thing is basically constructed to keep the quantum computer very, very cold. 15 millikelvin. It's the coldest thing basically in the universe. It's colder than outer space.
So inside that is 15 millikelvin.
Yep. So here, let me show you the one that we can like play with. This is it.
This is a quantum computer.
This is a quantum computer. The quantum computer is a chip in this one here, but this whole thing keeps the quantum computer working at insanely cold temperatures like we talked about.
So this is all refrigerator technology.
So all of these cables that you see here on the side carry signals down through the fridge into the processor, and then they do their quantum stuff, and it comes up, and it goes to these room temperature control electronics, and they turn it into things that humans can understand.
That is a quantum computer. We were allowed to touch it, which was cool. Oh my God.
So I think it's really funny that when people generally talk about like the difference between classical and quantum computers, people are like, okay, well you know how a classical computer works, right? But like the truth is that like nobody knows that. A simplification of it is it comes down to bits. And bits are made out of pieces of silicon, and you have, tens of thousands of millions of them in your computer. And they can either be in the state 0 or 1. We call it the ground state or the excited state. And everything that you type into your computer, like all words, all numbers, all colors, get translated into computer speech. But it's very binary, right? A quantum computer is run on qubits.
Qubits aren't like bits. They aren't a 1 or a 0. They're more complex. Think of this like a wave. A qubit could be really likely to be 0, which means a lower energy wave, or it could be really likely to be 1, which means a higher energy wave. And each qubit has a probability of being each. When a quantum computer is working, the probabilities of multiple qubits interact.
And they add constructively or destructively, just like waves would. If you were to like tap like two places in a pond.
You know how when you like explain something to a 2-year-old and they keep going why, and they have to explain again and you go why? Yeah. My question is, as the controller of the computer, you decide what about those probabilities?
Basically, you are altering the probabilities while you're running an algorithm.
It's a common misconception that quantum computers try all the options. That's not right. This is simplified, but it's more like a quantum computer kind of watches the pond. It watches how all of those waves interact and then finds the most likely answer. If this is all confusing, don't worry. All you really need to know is that quantum computers calculate things very differently than classical computers do, and that makes them good at different things.
Quantum computers are not going to be faster at everything than a classical computer. Like, it's not good for addition, right? Because your calculator and your phone is perfectly good at that. But the things that quantum computers are good at is finding structure. Than a classical computer. Like, it's not good for addition, right? Because your calculator and your phone is perfectly good at that.
Good at different things. Calculate things very differently than classical computers. All you really need to know is quantum computer all the options. That's not. It's a common misconception that quantum computers
You're an original. So is your Ozempic. Get your Ozempic savings card at ozempic.ca.
Babies don't ever stop. And behind them is an unstoppable Pampers 360 diaper with up to 100% leak-proof fit. Because they're Pampers, behind every baby. Now with new Easy Off tabs.
You're going to get an astrophysicist explanation of the literal three-body problem without reference to anything that's shown up on streaming services.
And that means he's not going to ruin the show for you.
I don't know anything about the show, but I do know enough to describe the three-body problem to you. Coming up. let's start simple.
Okay.
Okay. So as we know, the moon. Let's start simple.
Okay.
Okay. So as we know. The moon orbits the Earth.
Right.
But that's not the right way to say it.
Okay.
Okay?
All right.
The moon and the Earth orbit their common center of gravity.
Ooh.
So Earth is not just sitting here.
Right, and the moon is going around.
They feel in their common center, you know where it is? It's 1,000 miles beneath Earth's surface, along a line between the center of the Earth and the center of the moon.
Gotcha.
So as the moon moves here, that center mass line shifts. Okay? So that means Earth is kind of jiggling like this as the moon goes around.
Gotcha.
That's their center of mass. All right. This is the two-body problem. It is perfectly solved using equations of gravity and mechanics.
Makes sense.
Perfectly solved.
Yeah.
Isaac Newton solved it.
Okay.
My boy.
That's your man.
So that worked. Then Isaac applied the equations to the Earth-Moon system going around the sun.
Okay.
Okay? That works too. So in that system, let's ignore the moon for the moment. It's Earth going around the sun, another two-body system.
two-body
All right? But then he worried. He said every time Earth comes around the back stretch and Jupiter's out there,
right?
Jupiter will tug on it a little bit.
That's a lot of gravity.
A little bit. Tug on it as we come around back the other side.
What's up, Earth?
All right, and then it comes around again, tugs on it again. What's up, Earth? Right. And of course, everybody's moving in the same direction around the sun, so the Earth will have to go a little farther in its orbit to be aligned again with Jupiter, but it's going to tug on it. Okay. He looked at all these little tugs and he says, I'm worried that the solar system will go unstable.
Right.
Because it keeps tugging on it, it keeps pulling it away. The previously stable orbit would just decay into chaos.
Okay.
Okay. He was worried about this.
Okay.
You know what he said? But I know my stuff works, and it looks stable to me.
Right.
So clearly it is stable, even though it looks like maybe it wouldn't be stable. You know what he says? He said every now and then God fixes things.
Well, there you go.
That's the answer.
Even Isaac Newton. Wow, look at that.
Yep.
When in doubt.
When in doubt.
just let God figure it out.
Right. I can't figure it out.
God did it.
Clearly, we're all still here. And we haven't been yanked out of orbit by Jupiter.
Right.
But Jupiter is pulling on us.
So it's a God correction.
God correction. Okay. This is the first hint that a third body is messing with you. Right. Okay. In some way that maybe is harder to understand. Fast forward 113 years.
Okay.
We get to Laplace. He studied this problem.
Right.
Okay. And he developed, I don't think he invented, but he developed a new branch of calculus called perturbation theory. Okay. Unknown to Newton, even though Newton invented calculus.
Right.
He invented calculus.
Right.
All right. So he could have done it. He could have said, in order to solve this problem, let me invent
more calculus.
More calculus.
I just need more calculus.
Didn't do it. Didn't do it. So Laplace developed perturbation theory, and it comes down to we have two bodies, the sun and the Earth in this case, and the third one, the tug is small, but it's repeating. It's not a big. Jupiter's not sitting right here.
Right.
It's way out there. Way out there. It's just a little tug, and so you can run the equations in such a way and realize that a two-body system that is tugged often by something small, that it all cancels out in the end.
Gotcha.
Okay. So when it's out here, the tug is a little bit that way, but now it's over here, and the tug is less.
Right.
All right. And then sometimes it's tugging you in this direction when that's the configuration. You add it all up, it all cancels. Now it's over here by something small that it all cancels out in the end.
Gotcha.
Okay, so when it's out here, the tug is a little bit that way, but now it's over here, and the tug is less.
Right.
All right, and then sometimes it's tugging you in this direction when that's the configuration. You add it all up, it all cancels out. But Newton could not have known that without this new branch of calculus.
Okay.
Okay, perturbation theory. So that took care of that third body.
Gotcha.
Where solar system is basically stable. Okay, for the foreseeable future, in ways that Newton had not imagined, in ways that Newton required God.
Right.
Okay. Oh, by the way, just a quick aside. This is now up to the year 1800. You know who summoned up these books to read them immediately? There's a series of books called Celestial Mechanics.
Okay.
Napoleon.
Napoleon.
Napoleon, who read all the books he could on physics and engineering and metallurgy.
Yeah, look at that.
Okay, he wasn't just a tyrant.
Right.
He was like
a smart tyrant.
All right. So he summons up the book. Doesn't have to be translated because they're both in French.
Right.
He reads it, goes to Laplace and says, Monsieur, this is a beautiful piece of work, brilliant, but you make no mention of the architect of the system. He's referring to God. And Laplace replied, Sir, I had no need for that hypothesis.
Ooh.
5 medium specialty pizzas at Little Caesars, each just $9.99.
Specialty. Ooh, that's a mic drop. Ooh, that is tough. Man.
That's a dig on Napoleon and on Newton.
Yeah.
And on Newton.
I have, oh man, look at that. Yeah,
all right, so let's keep going.
Go ahead.
So now, let's say we have not just a planet and one of its moons, but let's say we have a star and another star, double star system.
Right.
Famously portrayed in what film?
Star Wars.
Star Wars.
Yeah.
All right, of course. So those two suns and the planet is stable, and I'll tell you why in a minute. But if you take a third sun, and put it there, about approximately the same size, then what kind of orbits will they have? Give me 2 fists here, okay? So I'm feeling this one, but now I feel, where's my gravitational allegiance? Am I going to come through? But then am I going to go that way or this way? So I'm coming into the system, and do I go to you in orbit? But wait, and you're still coming around here? Now I feel this. And so it turns out the orbits of a 3-body problem are mathematically chaotic.
Yes, I was about to say, that did not seem very stable.
Something has to give.
Well, this is in the series.
I haven't seen the series. I know. I'm just saying, something has to give. 2 of these are going to collide. One is going to get ejected. Okay? That is the classical 3-body problem. 3 objects of approximately similar mass trying to maintain a stable orbit. And it goes chaotic with just 3 objects.
Look at that.
It is unsolvable. You can, let me say that differently. You can calculate incrementally what's happening and track it until the system dies or splits apart or whatever. But you cannot analytically predict the future of the 3-body system, because what chaos will do for you in your mathematical model is if you change the initial conditions by a little bit, the solution because what chaos will do for you in your mathematical model is if you change the initial condition by a little bit, the solution diverges
further down the line. It goes
crazy. It's not just a little bit different later on down the line.
It is exponentially different.
Correct. Wow. With the smallest increment of distance. So I'll say, I'll move you in this direction, in this model, and then in a slightly different direction in the other model, it goes chaotic. That's what we mean by chaos. Okay. It's mathematically defined. Okay. So now there's something called the restricted 3-body problem.
Oh, right. Okay.
The restricted 3-body problem.
Never heard.
You have, give me your two things.
2 planets.
You got that. Okay.
2 bodies.
You got your 2 bodies. Now, the 3rd body is little. Now, you 2 will orbit each other. Okay. And then this, it's not messing with them. So this restricted 3-body problem, we have 2 masses of approximately equal, and one that's much less than the other 2. That is solvable. So the restricted 3-body problem.
Gotcha.
In the Star Wars case, that's the restricted 3-body problem.
Because you have the 2 stars and you have the little planet.
The little planet, there it is. And it's even better because the planet is so far away that it only really saw one merged gravity of the 2 stars.
Okay.
You're far enough away. That difference is not really mattering to you. You maintain one stable orbit around them both.
Around both stars.
Both stars. Okay. Now, if it got really close, then you'll have issues. Because then, again, gravitational allegiance matches stars are not going to care, but you will, because you'll get even.
You don't know where to go.
You don't know where to go.
I'm in love with 2 stars.
You'll have issues. Because then, again, gravitational allegiance matches stars are not going to care, but you will, because you'll get even.
You don't know where to go.
You don't know where to go.
I'm in love with 2 stars.
Because then, again, gravitational allegiance matches stars are not going to care, but you will, because you'll get even.
You don't know where to go.
You don't know where to go.
I'm in love with 2 stars. And I don't know what to do. Which way do I turn?
So anyhow, so the 3-body problem, the takeaway here is it's unsolvable.
Yes.
Not just because we don't know how to do it yet, because it's mathematically
It's built into the system.
The system is chaotic.
Yeah.
Okay, unless you make certain assumptions about the system that you would then invoke so that you can solve it. And so one of them is a small object around bigger ones. Another one, oh, by the way, in this solution with Jupiter out there, slightly tugging. It turns out over a very long time scale, this is chaotic. But much longer time scale than Newton ever imagined. Okay. Because yes, we are small compared to the sun, but Jupiter isn't. All right. And we're trying to orbit between them. Right. So that's why it's not deeper than that.
It's not.
Okay. Because yes, we are small compared to the sun, but Jupiter isn't. All right. And we're trying to orbit between them. Much longer time scale than Newton ever imagined. imagined.
Okay.
Okay? Because, yes, we are small compared to the sun, but Jupiter isn't. All right? And we're trying to orbit between them.
Right.
Right? So that's all. It's not deeper than that.
It's not, yeah.
Right? I could say the four-body problem, but this problem begins at the three-body problem.
Right. Because you're going to have the same thing in 4 bodies or 5 bodies. It's going to be the same.
And we have star clusters with thousands of stars in them, and they're all just orbiting. We can model it, but we cannot. Thousands of stars in them, and they're all just.
Or 5 bodies. It's going to be the same.
And we have star clusters with thousands of stars in them, and they're all just orbiting. Thousands of stars in them, and they're all just.
It's going to be the same.
And we have star clusters with thousands of stars in them. And they're all just orbiting. We can model it, but we cannot predict with precision where everybody's going to be at any given time.
Okay.
Because it's chaotic.
The chaos. So it's basically about the chaos.
It's all about the chaos. Yeah. So what we do is we model the chaos.
Right.
We say this will be statistically looking like this over time. You're not going to track one object through the system for eternity. That's not going to work.
That's so cool.
Yeah. All right.
That is so cool.
There it is. All right, another explainer slipped in torn from the pages of science fiction.
Yes.
Just a simple description of the three-body problem. Until next time. Looking up.
Build it like Beckham.
With a large welcome bonus, CIBC Aventure Infinite gets you on your next trip faster.
So So, Chuck,
yes,
we haven't talked about God in a while.
Oh, there's a reason for that.
Yeah, just that the history of civilization, anytime people had gods that they revered, they're in high places. The heavens have been associated with deity from the beginning.
Right.
Okay? And so my field, astrophysics, directly confronts many people's questions regarding our existence.
Right.
For that reason.
Mommy, where's heaven? Oh, it's up there. No, it's not, because I have a telescope. It's not up there, Mommy.
Right. So you have that intersection of people's curiosity and what actually happens in modern astrophysics.
Okay.
And if you are religious or prone to be religious, it's
Which I
easy.
think everyone is.
But perhaps, yeah, we're human.
We're prone to
It's a
be.
human thing.
It's a human thing.
Given how prevalent it has been.
Exactly. Throughout our entire existence.
Exactly.
And some of the earliest recordings of communication involve exactly that.
Correct. The burial rituals of Neanderthal, for example.
Right.
You can only have done that if you thought there was an afterlife or supernatural force.
Yes.
There's an urge, I think, to see that which is unknown in the universe. You hear of it. Big unknowns like dark matter and dark energy. Two hugely mysterious pieces of modern astrophysics that are unresolved.
Right.
And they're not little, they're big.
Okay.
You add them together, it's 95, 96% of what is driving this universe. We have no clue what it is.
That's insane.
No clue.
That makes me feel like we're the mistake. I'm just saying.
Because we're not the majority of the
when 97% of the stuff that's there is not you, probably don't belong there.
Yeah, Chuck.
Yeah, I'm just saying.
Anyhow, so we can measure them. It's not a mystery that's there.
That is there.
All right. We can measure their existence. We don't know what it is.
What it is.
All right. And there's precedent for that. We knew about the spectra of stars as soon as we were able to bring a spectroscope to the telescope. So there's interesting information here. We don't understand it, but we know it must be important. It's different for this star than that star. Oh, these two stars match. Let's make a catalog of all the spectra. Later, we would learn quantum physics, and we could then interpret what was going on. And thus was the birth of our modern understanding of stellar evolution. The first steps are the measurements. So it's not so weird that we have measurement and don't know what it is.
Right.
So there's not only that, there are other questions that are just simply yet to be answered, as opposed to mysteries. So one of them is what was around before the Big Bang. It might have been a multiverse, but even if there is a multiverse, what was around before the multiverse? Okay? And we don't yet know how Earth went from organic multiverse But even if there is a multiverse, what was around before the multiverse? Okay. And we don't yet know how